Right. Are we all here, I guess? Um, let's get started. Are there questions about anything we've talked about so far before we start? Doesn't look like it. So I wanted to start with just clarifying a couple of things. One was there was this question about the Chor-Mason magnetic monopole yesterday, and I said something which was not quite correct. So I looked it up. Turns out it's not a soliton in SU2 theory, but if you have there's what we call a Dirac monopole for just electromagnetism, which is just a singularity, and the singularity is resolved maybe in some far UV theory. So what you can imagine is having a Dirac monopole for hypercharge, and so the core of it is some singular thing, which is maybe the size of the core is far UV, way above the electroweak symmetry breaking scale. And that object dressed up with SU2 fields is called the Chor-Mason monopole. So it's not, so that's why it doesn't follow Ed's classification of solitons. It's not a solitonic object, purely solitonic object in electroweak theory. It's like a Dirac monopole on top of a solitonic object. Uh, yeah, that's possible. That's possible because that it's like it contains a hypercharge magnetic monopole, and so depending on it's different from the gut monopole case. Like if you have a gut monopole, its magnetic charge versus the Chor-Mason magnetic charge is different. Do you think? It might also be because of yeah. So I didn't. We can look at the quantization condition, but the resolution of the puzzle. Why does a monopole exist where SU2 cross U1 broke onto U1 does not have the second homotopy group is because it's not really a soliton. It's really like a singular configuration. So if you UV completed it, then you would have the second homotopy group to be non-trivial, and then it would be a soliton in the full UV theory. Another thing I sort of should have emphasized, but I didn't really, was this. Uh, Connection between Dashen and Yang-Mills. So what we said was that for certain ranges of parameters in the Chiral-Lagrangian, which was m up, m down, bigger than something like this. For this, we have a Dashen phenomena where if you plotted the vacuum energy in the Chiral-Lagrangian as a function of theta, we would see that there's branch crossings at theta equals pi. And we said there's a similar phenomena in Yang-Mills, where pure Yang-Mills, no quarks, where there's branch crossing and there's a cusp at theta equals pi. So we said that, and we showed that these were sort of similar in spirit objects. This was all, they were both coming about as a result of there being a CP symmetry, but two solutions changing, the branches changing as you go across theta equals pi. So that is the similarity, but there's an important and cool distinction between them. In the Yang-Mills case, this is actually quite an interesting cusp. So this cusp is actually associated with deconfinement. Whereas, whereas this is not, okay? So if you imagine the theta was actually a dynamical variable, so it was an axion. This, what we're plotting here is what happens as you have an axion domain wall, right? And so in pure Yang-Mills, on axion domain walls, QCD, the Yang-Mills theory is deconfined. And again, we can show it using the sort of one-form arguments that we were talking about, whereas it's not true in the Chiral-Lagrangian case. Okay, so even if Dashen phenomenon existed in the standard model, we would not have deconfinement on QCD. We would not have deconfinement on QCD axion domain walls. So there's a crucial way where these are different, but they also have the similarities that we pointed out last time. Okay, any questions about that? Good. Okay, so our task for today is to talk about solutions to the strong CP problem, and we'll start with a solution that isn't really viable, but it is actually quite instructive to go through it, and it's called the massless up quark solution. And this is something we talked about when we talked about anomalies. We said if one of the quarks of the standard model was massless, then you can do a chiral rotation. That's a symmetry of the Lagrangian. The chiral rotation is anomalous, so you can shift the theta angle by this chiral rotation, and so you can get rid of the theta angle altogether. So theta is unphysical, and so that would be a solution. Those were the words we used. So let's think about those slightly more carefully. So there are two sort of puzzles a priori when you start thinking about the massless subquark. So this was, which is first is, let's say, if you work out the sum rules for pion masses and kaon masses, you can figure out the ratio m up, m down, which is around 0.5. If you do fit to meson spectra at leading order in the chiral Lagrangian. And this was known for a very long time, probably 70s, even if not earlier. But people were entertaining the massless subquark solution as late as mid 2000s. So this would have suggested that meson spectroscopy already told us the quark was not massless. So why was it still a viable solution as of 2000, whatever, 2005? So it was viable before Lattice ruled it out in 2005. So why is this not sufficient? That's for the first puzzle. And the second puzzle is with our argument for rotating the quark, rotating the phase of the up quark and getting rid of the theta angle seems a little singular. So if the up quark mass is 0, then we rotate the phase and the phase completely disappears. What if the mass of the up quark was 10 to the minus 500 GeV? I mean, it sounds ridiculous that should not solve the strong CP problem, but it seems like our argument that we can rotate the phase of the quark mass, the phase of this very small modulus seems to now be physical, right? So it's a little confusing, or appears a little confusing to say exactly zero mass modulus does not solve the strong CP problem. There's no phase associated with it. You can rotate the phase. The phase of 0 at the origin is unphysical, but the phase of anything which is not at the origin suddenly becomes physical. So that seems puzzling. So who knows the resolution to these? Who's seen the resolution to these puzzles before, or knows them, or can figure it out live, which would be quite impressive. Well, Michele is not answering. I'm sure he knows that. Are the puzzles at least clear to people? That why is there an apparent paradox in the thing, or not? The questions about the issue. Yes. Which one? The first one, the second one? There are two. So first of all, there are two puzzles. So there's two puzzles. One is that we can use the chiral Lagrangian to figure out you can use the chiral Lagrangian to match to the QCD Lagrangian. So even without doing lattice calculations, we have some handle on getting the m up, m down values out. And so if you do the leading order calculation in the chiral Lagrangian, you find that m up is not 0. It's actually half of them down. And so, but that is not what rules out the strong CP problem solution. So that's one puzzle. Why is that piece of data not already telling you that this could not work? Why do you need to go to lattice? That's the first puzzle. The second puzzle is that our description of doing this chiral rotation to get rid of the phase the language seems a little singular in the sense that you could do the chiral rotation and say the quark mass is 0, so that the phase doesn't show up anywhere, so you can get rid of the phase altogether by doing a chiral rotation using the anomaly. But if the quark mass is arbitrarily small, the phase doesn't disappear. And so then, does it still remain physical or not? And so how is that process smooth with respect to m up going to 0? Not exactly 0. Okay, those are the two puzzles. Right? So, so anybody, anything? Yes. Which scheme meaning? Um, well, so on-shell mass for a quark wouldn't quite make sense because so what we really want to yeah, so it would be if you write down the QCD, it would be some mass parameter, choose some renormalization scheme where let's say there's some Green's function at 2 GeV or something where QCD is relatively perturbative, and define the propagator there, and the pole, the mass appearing in the Lagrangian in that scheme would be the perturbative definition of the mass parameter. We could also think about the Yukawa coupling itself, the Yukawa matrix, if you just want to do the high energy thing. So one eigenvalue of the Yukawa matrix being 0 would be another way to say it, and the other one would be whatever Carrel Lagrangian, whatever parameters appear in the Carrel Lagrangian, and that you could even talk about on-shell pion masses and things like that. So, but the resolution to the puzzles is related to your question in a way. So the first puzzle, the resolution is one resolution is that uh, there's what is called Kaplan-Manohar ambiguity, and the idea is that this statement I said was true when you try to match. So what we're trying to do is we are saying let's say it like slightly more precisely. We have LQCD, which is G mu nu G mu nu. Um, for talking about the massless subquark, actually it will be sufficient to just no. Actually, let's keep everything. Um, I was gonna say we just keep the upquark, but it's just cleaner to just keep everybody. Um, so let's work in this approximation, the 3-flavor approximation, where we keep only up, down, and strange quarks. And perturbatively at a few GeV, let's say QCD is perturbative enough that we can, in some UV renormalization scheme, we can define these parameters, and that defines our Lagrangian in the QCD. And what we want to do is in the Carrel Lagrangian, we want to match this to, for example, the leading order term, which we wrote down yesterday, which is trace mu plus Hermitian conjugate with some undetermined coefficient. So the leading term in the Carrel Lagrangian that would be sensitive to these Carrel symmetry breaking effects would be this operator, and this is how you would deduce m up over m down is 0.5. But it turns out that if you wrote down the Carrel Lagrangian to second order, so one higher order, there's an ambiguity, and you can see there's an ambiguity because uh, um, the chiral charges of the Spurian m up and m down m strange over lambda QCD squared, I guess lambda QCD. The chiral charges of these two objects are exactly the same. The determinant, it's an SU3 cross SU3 chiral Lagrangian, so the determinant is, the determinant does not carry any SU3 cross SU3 charge. So the Spurion, wherever M up appears, in Spurion analysis, a higher order term with MDMS over lambda could also appear. So if you actually try to extract these parameters at higher order in the Carrel Lagrangian, you'll find that there's an ambiguity, and so you can't unambiguously say that the meson spectra tell you that the UV parameter M up is non-zero. Okay, so that was off the bat the first reason why people took this possibility seriously, even though naively you would have said this is not possible. Okay, and yeah, so let me say reference. I didn't write down the actual references. I'm collecting a list of references. I'll put it on Slack. So the relevant references for massless subquark is there's a paper by Georgi, which is an old paper, and there's a paper by Dine and Draper, which is a more recent paper. There's a paper by I think Banks. Neer and Seiberg, and these papers are where all this discussion is laid out in. So just by meson spectroscopy, you can't break this degeneracy. If you did more measurements, or if you had something like lattice, you could pin down various coefficients at even higher orders in the chiral Lagrangian, and then once you do that, you find that this actually this option of having up quark being massless is ruled out at 3 sigma or something like this. Okay. So that's one resolution. What about the resolution of the second puzzle? And that also has an interesting story. Bits are falling off of the microphone. Um, right. So the second part of the story, where we say, what, why does it look weird about insisting on m up equals 0? It's the first thing to realize is that m up equals 0 is not a special point. Okay. What we mean by special point is something that is invariant under redefinition, different RG schemes. If that something like that is true, then they would say that that's a physically well-defined point. But m up equals 0 is not such a point because the chiral symmetry is explicitly broken by QCD effects. And so if you set m up equals 0 in a certain renormalization scheme at a certain scale, it will undergo additive renormalization, and it will not be true anymore at a different renormalization scale. So saying m up equals 0 is not really a physical constraint you can put on your theory. It's a statement about it's a scale dependent renormalization scheme dependent statement. Unless there's a symmetry protecting your parameter, this is usually true. It undergoes additive renormalization, and so a particular value of the parameter is a scheme dependent quantity. Okay, so what is this additive renormalization? What does it look like? That's what we want to look at and understand. And that will give us some insight on how m up equals 0 solutions look like. Okay, so the chiral symmetry we said before has an ABJ anomaly so that the current associated with the chiral symmetry is proportional to the GG tilde term in of gluons, and as is true for any anomaly, this term is a topological term. So if you just talk about topologically trivial field configurations, there is no violation. But on non-trivial topological field configuration, this is an explicit violation of the symmetry. And non-trivial topological configurations, by now we're good friends with them. They're called instantons. So the idea is that instantons, in presence of instantons, we will see explicit violation of this chiral symmetry. And so the instanton effects will generate for us an additive renormalization for the up quark. Okay, so these instantons, we won't construct these instanton solutions in great detail. They're analogs of the instantons we talked about in particle on a circle. In particle on a circle, there's just a quantum mechanical variable, so there was just time dependence, and they were localized in time. They're analogs of the solitons or tunneling events that Ed's talking about for all his topological defects. So the instantons in gauge theory are localized field configurations. They're directly analogous to the ones we talked about in particle on a circle. So instantons are let's say in SU3 color. These are solutions to Euclidean field equations. Just like our instantons in particle in a circle were classical solutions um, to the Euclidean equations of motion of a particle on a circle. In this case, they are localized in space-time. So they have a time localized. They're localized in time as well as in three-dimensional space. So they're really like space-time events, like tunneling events in space-time, and the ones we'd be interested in are O4 symmetric. So they have a symmetry, which is when you look at the Euclidean solution, there's the Euclidean field equations have an O4 symmetry. The solutions have the same O4 symmetry here as well. And these are characterized by the homotopy groups. SU2 has in it S3, and when you look at space-time with one-point compactification, it has a non-trivial homotopy group, and so the instanton numbers are classified by homotopy groups completely uniformly with the classification Ed was telling you about. And what other features? Yes, so remember when we were talking about the particle in a circle instanton configurations, we had zero modes. In that case, it was just the time, the position, the instanton could occur at any time, and so we had an integration over this time coordinate. Again, the zero modes appeared in Ed's lectures as well. So there are zero modes on an instanton background. These are parameters that classify the instantons which do not affect the solution. So for example, in 4D space, we could localize the instanton at any point in 4D space. The translation invariance tells us that these would be solutions for every possible value of the origin of the instanton, the center of the instanton. And so these are zero modes, which we integrate over in the path integral. So we would get an integral over zero modes. And the zero modes in the case of the instanton solution for color are the position, the center of the instanton, and there's an extra zero mode, which is the size of the instanton. So the solution has an extra scale invariance, these classical solutions to Yang-Mills equation. And so there's an extra parameter called rho. And so when we do our path integral, we'd have an integration d for x. This would just be the integration over the position over the instanton. And then we would have an integration over d rho of the instanton size. And this is directly the analog of the dt integrals that we did in the case of particle in a circle when we inserted arbitrary number of instantons and we integrated over their time coordinate. In this case, we integrated over all the 4 zero modes and the fifth one as well. Okay. So just like anomalies, there could be a whole course on instantons. Ed is giving you 1/4 of that course already. So this is to show you the connections of the strong CP problem and the ideas in the strong CP problem with topological defects and instanton physics. This is not supposed to be self-contained in any form. It turns out when you have light fermions, maybe I can write here. You also have additionally fermionic zero modes. So zero modes localized, whenever we talk about any kind of topological defect, what we're doing is we're taking our original theory, we're writing down a path integral around that topological defect, some classical Euclidean solution, and we're doing a fluctuations around that semi-classical saddle point. We find that fluctuations around that semi-classical saddle point have so-called zero modes that don't affect the solution. The bosonic ones we just talked about, but often they're also fermionic zero modes. And this is related to beautiful physics and mathematics, related to the Atiyah-Singer theorem. Various kinds of defects have their fermion zero modes attached to them. The kind of defects, for example, axion strings that Ed has been talking about, often do have fermion zero modes attached to them. So the actual axion strings have massless chiral fermions living on them. And so these strings become superconducting as a result of that. Okay, so there's very cool phenomena associated with zero modes on every kind of topological defect. They can also be measured using topological data, using the index theorem. And so this is again advertisement to maybe dig deeper into this if you haven't encountered this. Okay. So there's a uniform, just like the homotopy groups uniformly give you a classification of all kinds of topological defects for any d-dimensional defect in any capital D number of dimensions. The same is true for zero modes counting, especially fermion zero modes counting. You can classify using topological data how many fermion zero modes you expect in a given topological background. So so what's the upshot? What the upshot is, what instantons look like is it looks like a term in the Lagrangian. Remember, if you're doing the partition function, then we get an integral d for x L, our partition function. If you have an interaction term, let's say we have some integral over our fields, whatever, e to the I, the free part, e to the I L int d for x. And in perturbation theory, we can expand this, and in perturbation theory, this would look like right? 1 plus that, I guess. And so when we're doing a partition function around an instanton background, the integral over this d for x just really looks like a new kind of interaction term, and this is called the 't Hooft vertex. So the effect of the instanton can be captured by adding an extra vertex in your effective theory, and the instanton provides you with an extra term in the Lagrangian, so to speak, which captures all the effects of the instantons. So we want to eventually look at the renormalization of the up quark. We know how to do Feynman diagrams. 't Hooft tells us actually instantons are complicated, non-topological objects, non-perturbative objects, but their effects can be captured by a perturbative vertex in your Lagrangian. You can use that. You can do RG as you would in a different theory. So that's the utility of this formalism. What does a 't Hooft vertex look like? It's a vertex. And it has fermion zero modes. So in this case, we'd have a fermion zero mode for every light fermion that you have in the theory. So this would be U. So every Weil fermion you have in the theory, so U conjugate. These are all Weil fermions. D conjugate, S conjugate, with the arrows pointing all out. So they're all left-handed Weil fermions. The whole point of the 't Hooft vertex is that it violates chirality. Okay, about these many units. Have people seen the 't Hooft vertex before? Anyone seen the 't Hooft vertex before? I'm surprised Ed hasn't seen it before. Right, and the strength of this vertex is given by e to the minus the classical action of an instanton, which turns out to be 2 pi over alpha s. Which alpha s? We'll talk about that in a second. So that's the classical action. If you could take the classical solution of the Euclidean Yang-Mills equations, you can plug it in. You can find the action for the classical action for the instanton, and that's an exponentially small quantity when you are at weak coupling. So it's it goes like e to the minus 2 pi over alpha s. There's some numerical constant which I'm not going to bother with. Actually, let me write it like this first. So the vertex looks like the term in the action looks like d for x, and there's an integral over rho, d rho over, let's call it rho to the fifth, and you get all the quarks, so I guess psi conjugate cubed, times some function d of alpha. Did it properly. Sorry. Just giving myself more space. D for x. D rho over rho to the fifth. Just for having a dimension 4. So the row counting is just going by dimension at the moment. This quantity u psi conjugate cubed. D of alpha s evaluated at the scale 1 over rho. And this needs some power rho cubed. Okay, so we have an integral over d for x, that's the zero mode for the translation. There's an integral over the size. The powers of size come out just by dimensional analysis. We have 6 fermion fields sticking out, so it's a 6 fermion vertex that we get. And then we get some e to the s classical, like we got in the case of the particle when we're expanding around a classical solution. We get the e to the minus s classical term in the potential. And then an important term that I should write down explicitly is for every instanton, we get a factor of e to the I theta. Question, yes? What, sorry, what is? Rho. Oh, good. So if you look at the solution to the Euclidean Yang-Mills, you would find that there's a, it looks like something like, it has a parameter rho, which is basically setting the size of the instanton. So for every rho that you find a different solution to the Euclidean equations of motion. So just like you could center the instanton anywhere in space-time, you could also change its size. So there are 5 zero modes for the instantons, and when you do this expansion around a semi-classical solution, you get an integral over every zero mode you have. And so the rho integral is just the integral over the size of the instanton. So rho is the size of the instanton. So if we're calculating the classical action, we should probably calculate it at the size of the instanton. So the correct scale for alpha s to be calculated is roughly the size of the instanton. And so that's why alpha s is evaluated at the size of the instanton here. Yeah? Oh yeah, so this is, I mean, so if you do the zero mode counting, you just find that the rows work out with the to be dimensionally consistent. Yeah. So I haven't shown you why there's row dependence, but you actually look at the modes. You look at the fermion zero modes, their normalizations, then eventually dimensionally it should work out. So the rows just work out dimensionally, but they come from normalization of zero modes of the fermions. Question? Yes. Sorry. Good. So we'll talk about the. That's a good question. The question is, yeah, we haven't said dilute instanton gas, but when we're doing this, we're doing when we did the particle on a circle. That's what we did. We said we can scatter instantons and anti-instantons, and they're independent of each other, so we can just add them up. And that was the dilute instanton gas approximation, and that's a similar spirit to what we're doing here. This is the dilute instanton gas approximation is good when the typical number of instantons in your configuration is small, it's dilute, and it's small when the probability of producing an instanton is small. So when this, whenever this factor is really small, which is true for weak coupling, dilute instanton gas approximation is okay, and this approximation would fail, and quantitatively we would not have control over this calculation when QCD becomes strong. So this is what we said for the theta dependence of instantons solving the instantons giving mass to the eta prime. It's the same idea where instantons can give mass to the eta prime in the dilute instanton gas approximation. Once you get to strong coupling, then we lose control over that calculation. So we can't really say in any reasonable sense that that's the right picture. Okay. Other questions? Uh, d of alpha s here is just some constant. So this means this is some function of alpha s. The crucial dependence is this classical action of alpha s uh, evaluated at the size of the instanton. Yeah. Okay. Let me just say that. And then there's some constant factor which I'm not going to write out in detail. Okay. So what this tells you is that at least at energies where QCD is perturbative, we get an exponentially small strength vertex, which actually gives us dependence on theta. This is actual explicit dependence on theta in the Lagrangian, and you can see explicitly it violates chiral symmetry. It ties up U and U conjugate. Okay, and so this will generate a mass for the up quark, given that there's a mass for the down quark and strange quark. So if we just had a Lagrangian where the down and strange had masses but not up and down, then we would have a Feynman diagram which looks like this. So drawing them coming out. Because these arrows are along chiral fermions, the only way to close these loops is doing a mass insertion. But if I have a mass of the down or the mass of the strange, or if I had Higgs interactions, I could close up these loops, and this diagram looks like a mass for the up quark now. So down and strange generate a mass for the up quark, and the mass for the up quark they generate, unsurprisingly, is proportional to MD MS, which we already sort of guessed from just looking at the chiral charges of these parameters. Okay, they would have to be that because the SU3 cross SU3 chiral symmetry is not broken by the instanton vertex. So whatever it generates would better be consistent with the chiral symmetry, and indeed it is consistent with SU3 cross SU3 chiral symmetry. It only breaks the U1 chiral symmetry. Okay, so this is the 't Hooft vertex calculus. That is a mini industry, a micro industry now where people use this not just in the standard model but also in BSM solutions. This is one way to interface with generation of masses which involve a non-perturbative contribution as well as perturbative contributions. Okay, so this is a toy example where there's a few models out there which actually utilize this in the BSM context. So let's look at what the equation for the RG equation for MUP looks like, what this additive renormalization would look like schematically. Because as we discussed quantitatively, when we do this integral over all rho, as soon as we reach the instanton size of order lambda QCD, we will lose quantitative control of this calculation. But we can try to track it in the perturbative regime to see what it looks like. So say again, sorry? Yeah. You mean the up quark current? Yeah, yeah. I think this. I mean, I'm wondering if it's a basis dependent statement. Divergence of the current. No, no, yeah. So it does not show up. So yeah, sorry, it does not show up. Yeah, yeah. The axiom, so. Well, I mean, it's uh, um, if you imagine this was like a UV instanton, then and you got this quantity to be at 2 GeV, you would not generate a theta term, but you would have a, which I'm going to say, but you will be consistent with lattice. You would not be inconsistent with lattice if this contribution came. Let's say very far in the UV you had 0, and at 2 GeV this was the mechanism to generate the up quark mass. You would be consistent with lattice. That's a solution to strong CP. We get yeah. Let's yeah. Well, yeah. Let me say in a couple of minutes. So better, I've written down a couple more things, but um, like you could ask in particular, for example, let's say there was an axion in the theory, uh, and at low energies, very low energies, things are clear. All the quarks, all the QCD is gone. So d mu j mu 5 in that theory, what you want to track is really box A, right? And so your question is equivalent to asking, at least as low energies when it's unambiguous, it's asking whether the axion picks up a mass or not in this theory due to these kind of words. And it doesn't. The axion is massless. So in that sense, it doesn't show up. It doesn't show up. But then I have to think more carefully about the basis when their up quarks are present in the theory as well as instantons. So you have to do a more careful RG scheme maybe, but very low energies, it's 0. It doesn't show up. So that's why it is a solution to the strong CP problem. Anyway, so if that was telegraphic to people, I'm happy to flesh it out for other people. But so yeah, so what we're going to do was to look at the schematically what this actually looks like. So let's look at the evolution of the quark mass parameter between two RG scales. Let's say 2 scales, something like this. And this would be an integral over the size, this would be an integral over the size of instantons between those 2 scales. And it would look something, again, I guess there should be a twiddle here, schematically like this, because I'm not going to keep the order 1 numbers. Okay. And so the crucial bit, which is related to Michaela's question, is that the correction to the mass comes with the factor e to the I theta. This is an instanton correction, so it always comes to the factor e to the I theta. Sorry, question. Yes, I didn't in this case explain it in detail, but you should think of this in analogy with when we were talking about particle in a circle, and we said of a particle in a circle, whenever there was a winding number n trajectory, it came with the e to the I n theta. So really, in the UV, you can think of it as coming from, you have e to the I theta times, in the QCD case, GG tilde. And on an instanton with a non-trivial winding number, this is, on an instanton configuration, this is an integer n. And so for a single instanton, so this is a single instanton contribution that we're writing down. For a single instanton, there's always an e to the I theta that it comes with. Yeah, so yeah, so let's take a detour to emphasize this point because it's relevant. People talk about theta vacua and n vacua, right? And that language is very gauge dependent. Okay, so remember when we had a particle on a circle. This I think is important and subtle point, so that's why it's worth taking a small detour for that. We have a particle in a circle. We have a pendulum. The pendulum has one classical state pointing down. You make it quantum mechanical, then it's not one position, but it spreads out a little bit, right? So the pendulum always has one unique ground state to talk about. The quantum pendulum didn't have n vacua, theta vacuum. Vacua, there was one unique ground state, which was some wave function on this circle. Then when we talked about unfolding the circle, then there were all these gauge images of this of 0, and our quantum wave function was then some maybe e to the I n theta sum over n, where n was some function localized in one of the sectors. So in some gauge description, it could look like there's the theta vacuum, which is a sum over n vacua, but that's a description in this gauge. On a circle, there's a unique wave function, there's a unique ground state, there's no notion of theta vacuum. So also in QCD, there's gauges where you just have you fixed everything, there's no gauge redundancy, including no large gauge transformations, and there's a unique gapped vacuum around theta equals 0. Okay? Not theta equals 0. There's a unique gap vacuum for generic values of theta. So so the notion of theta vacua and n vacua is a language dependent and gauge dependent statement. For a given value of theta, we just have one vacuum, which we are expanding around. Okay? So yeah, this is so this is not always phrased with this language in the literature, so that's why it's worth spending time on. Okay? Any other questions? These are very good questions. If you can avoid talking about Nelson bar altogether, that would be great. So if you keep asking questions, and I can just, no, I'm just kidding. Other questions? Good. So the crucial feature that we wanted to highlight was this dependence on e to the I theta. And so what that means is that if you looked at the parameter, this complex parameter m up e to the I theta, this is the actual combination of parameters that shows up in theta bar, the arc det. More generally, if you want, more generally, it would be det m e to the I theta. That, remember, was the invariant parameter theta bar that shows up in neutron EDM and things like that. Here, let's imagine a basis where MDM and MS are, MU, MD, MS are all real, and so we're just talking about this. And let's just keep the dependence in M up, because that's the one we're contemplating being 0. So MD and MS are fixed, real numbers. So all the dependence on theta bar in our theory is encoded in this complex number, mu e to the I theta. And we want to just plot in this complex plane how its evolution happens. And you'll see that because the instanton vertex comes with a factor of e to the minus I theta, I haven't been careful with the signs, but the signs work out in the way they're supposed to. So trust me on the signs. I'm sorry, I probably should be to the minus I theta here, depending on how you define. The sign is such that exactly the combination theta bar that shows up in this equation. Okay, it's not a coincidence. So the effect of the RG evolution due to this instanton effect is to move you along the real axis in this plot. Okay, in fact, move you to the right generically. So while we said m up equals 0 is not a special point because it gets additive renormalization, the actual physical parameter that we care about gets a renormalization in a very particular way, which it gets renormalized along the real axis, and precisely because the renormalization happens through the instanton vertex, and so it doesn't change mu, the real part of m up equal e to the I theta. So this is now the phrasing of the up quark, massless up quark solution that I like. Imagine that you said the up quark was very small in the UV. It was small because in the UV, the instanton violation is exponentially small, and so it's a good symmetry to say m up equals 0, and any other explicit violation is also small. So you could say the m up lies in somewhere in the circle, but in an arbitrary phase. So any arbitrary complex number for m up is legal, and then from far UV, as you run down into the IR, you end up at some point here, and this is a result of instantons running from some UV scale down to the IR scale, down to the Chiral Lagrangian. And so the effective theta angle that you would see in the low energy theory is the argument of uh, this complex number, the renormalized low energy mass, which is a much smaller mass than, which is a much smaller number than this arbitrary number you started with. So this actually tells you that if you want theta bar to be order 10 to the minus 10, you want the original up quark mass to be order 10 to the minus 10 of the whatever this renormalization arm is, which is ordered, parametrically ordered MD. So again, the up quark solution by itself doesn't work in the standard model. So this is a little academic, but it shows you how non-perturbative effects have an interesting interplay with perturbative definitions of parameters. And in particular, this if you in this theory, you don't change this m up e to the I theta parameter by a complex number. Yes. Right. Right. So this argument so this argument really only works when it's perturbative, right? So imagine this is where you hit the QCD scale. So then the argument becomes qualitative instead of quantitative. But the fact that physics only depends on this particular combination, so you could put the theta angle in the mass of the quark matrix. So that tells you that everything would always appear in this combination. Once you put theta angle in here, the rest of the physics, all the non-perturbative physics, is CP conserving because there's no longer theta anywhere else. And so the fact that it would qualitatively be the same, even though quantitatively you can't use the instanton calculus to predict it, remains the same. See if they wanted anything else to say. Yeah. So at the end, at the end at 2 GeV, the up quark mass is not enough for chiral effects to actually push it down to the QCD effects to actually give you the right right low energy Lagrangian. So the up quark solution doesn't work in the real world, but UV modifications of QCD actually have some success, some limited amount of success in trying to get this to work. With the very far UV, the up quark is massless. In some intermediate scales, there's some enhanced effects that actually enhanced instanton effects that push you towards the right here, and then enough that by 2 GeV you are at the right ballpark for the lattice, what lattice tells you. Question? Yeah, I think it's always to the right because it's let's see, why is it always to the right? Honestly, to the left is like a theta equals pi contribution from QCD. So so I want to say that the contribution to this combination is real positive once you've decided theta equals 0 is the one where you have. So whenever you have fermions in your theory, what is theta equals 0 and theta equals pi is always tricky to define because you can always do a rotation of the quark mass matrix by e to the I pi by 2, and then you can get a theta equals pi being the being what was theta equals 0 in the previous thing. So there's a field redefinition that always makes theta equals 0 and theta equals pi basis dependent. Once you've chosen your basis so that theta equals 0 is the one where you have a unique gapped vacuum, so it's not the theta equals pi, that then defines your basis, and in that case I believe it's always to the right. But yeah, I haven't thought about it very carefully, so it's a good question. Okay. Good. So we're going to move on from instantons. We're going to move on to BSM solutions to the strong CP problem. So if this is your last chance forever to ask questions about instantons. No, we have questions and answers in the afternoon today again, so you can ask questions then too. So we're going to move on to talk about solutions to the strong CP problem, and and discrete symmetries as a class of solutions where we posit that there is some discrete symmetry in our UV Lagrangian, usually parity or CP, that explains why we don't have theta bar to start with, order 1 theta bar to start with, and then there's some model building involved to explain why we do have CP violation and parity violation as seen in the standard model, but not it doesn't bleed into generating a large theta bar. That's the sort of spirit of the argument. Um, so there's a question usually. Um, it is somewhat related to your question about the theta vacuum, maybe not quite, but um, so there's a question sometimes people raise whether discrete symmetries can even in principle solve the strong CP problem. Is there such a thing as a discrete symmetry solution to the strong CP problem, even in principle? And I wanted to give you just the qualitative explanation for what the issue is, and at least what my take on the issue. So remember when we were again talking about the particle in a circle, we said there was we said either we can decide we can put the we can decide the Lagrangian is half q dot squared plus theta q dot, or we could choose that our wave function had a twist. So either we could say our Lagrangian has a theta term explicitly present, and our wave functions are periodic, or we could say our the Lagrangian doesn't have the theta term, the Hamiltonian does not have the theta term, but our wave functions have this boundary conditions. This doesn't make sense. Our wave functions have boundary condition that when they go around the circle, they're twisted by a certain angle. Or equivalently, we could have also said that we do everything periodic, no boundary conditions on no theta term in the Lagrangian, but we posit this prescription that for every winding around every instant on winding, the prescription to sum over different winding sectors is to attach a phase e to the I n theta for every n and do the path integral as usual. And we said that these were all equivalent, mathematically equivalent ways to talk about the same underlying system, and we could choose one or the other. Okay. So in a description where the symmetries of the system arise from the symmetries of the Lagrangian, if you say that impose CP implies Lagrangian should be invariant. If that is your definition of imposing CP or theta, CP or parity, you would find that these three descriptions don't commute with that definition of a symmetry. For example, if you chose to work in this description and you said I'm going to impose CP, you'll find that you live at theta equals 0 or theta equals pi. If you chose this description, your Lagrangian does not have a theta term. You'd say I impose CP, but I still end up with a theta. I still end up with a theta in my answers. My vacuum energy depends on theta. I impose this CP symmetry, but somehow the state picked the theta angle, and so the symmetry is not helping me, right? So if you insist on this definition of what imposing a symmetry means, these things that we claimed were mathematically equivalent don't seem equivalent under that definition of the symmetry. Okay, is that clear with you? So really, I would say that we should think about symmetries as symmetries of the partition function. The partition function is the thing that has invariant physical information. So when we wrote down the partition function for our theory, we had this definition of the partition function, and all of these different ways of looking at the theta dependence of the theory shuttled the theta dependence either into the boundary conditions of this partition function, or on the Lagrangian itself, or just how we sum over the different sectors in the partition function. So if we said that so imposing CP is z of theta, so the partition function should be invariant, and so z of theta should be equal to 0. The imposing CP means that theta should be either 0 or pi, and the partition function that you see is that it's invariant under all these three notions of where the theta dependence comes from. So the usual criticism is that if you think about symmetry like this, you would say, well, CP doesn't do anything for me. CP doesn't solve this. CP symmetry cannot solve the strong CP problem even in principle, because the way I think about it, the whole theta dependence comes from states and not Hamiltonian. And so we should not even think about these discrete symmetry solutions of the strong CP problem. The point of view I'm advocating is that we should really think of symmetries in terms of partition functions, which then makes this whole point completely, throws away this whole point. These three are mathematically equivalent descriptions, and they commute with our definition of symmetry in terms of the partition function. And indeed, if we impose the symmetry on the partition function, and we said, I want my partition function to be invariant under CP, then you would find that theta equals 0 is preferred in this. Okay? Any questions about that? Certainly, the description of symmetries in the modern sense we were talking about, of generalized symmetries and higher form symmetries and etc., find the natural definition in terms of the partition function rather than Lagrangians. There's often not even a Lagrangian to talk about for some of these systems people study. So we should think about the partition function, not the Lagrangian as the king. The Lagrangian has fields. The Lagrangian is not even invariant under field definitions, so we should really think about symmetries and properties of our system as a function of the partition function, in which case this puzzle doesn't really arise. And you can think about theta dependence however you like, and everything commutes. Yeah, so I think I'm going to. Yeah, there was this. There's an interesting thing to just mention about imposing parity. So P or CP. So what parity does is takes all the spatial coordinates to minus themselves. That is the parity operation. And it's a space-time symmetry, obviously. It changes, it acts on space-time coordinates. And in 3 plus 1, or any odd plus 1 dimensions, this also reverses orientation. So it acts, which is also true for something called R, which is a reflection symmetry. So reflection about, so let's say x, y, z goes to x, y minus z. Okay. So both reflection and parity in three spatial dimensions change the overall orientation of your space. The thing that actually physically is relevant is this orientation reversal. In even dimensions, so in 1 plus 4 dimensions, for example, parity does not. Parity is actually part of the Lorentz 5D Lorentz group, so it does not reverse orientation. So when people talk about people talk about parity, and especially in the context of relating phenomena at various different dimensionalities, including condensed matter physics, which are sometimes 2 plus 1 dimensional systems. Sometimes we want to work in extra dimensions, so we are talking about 4 plus 1 dimensional systems. The thing that's the relevant thing that we want to track is reversal of orientation, and the thing that tracks that across dimensions nicely is R rather than P, the reflection rather than parity. But if you're content to work in 4 dimensions only, then we could always just talk about parity. But really, you should keep in mind that things look nicer and phrased in terms of reflection. In 4D, they're equivalent. Okay. C is an internal symmetry. And it's not as universal as parity. It's not a space-time symmetry. So it's sort of the given definition of theory could interchange your definition of what you mean by parity and what you mean by CP. Okay, so P versus CP is a matter of definition. You could choose your representation in such a way that that transform under parity in such a way that actually what you call P, I would call CP, and so on. But the thing that's invariant is that there's one space-time symmetry that reverses orientation. There's a standard definition of P and CP in the standard model. So I don't suggest you change that definition, otherwise you won't be able to talk to anybody. But keep in mind, C is an internal symmetry where there's some choice of what transformations you want to ascribe to your fields. Like any other internal symmetry, you can choose charges. And but parity or really orientation reversal is the symmetry that changes that changes the theta angle. So the thing that theta f tilde theta gg tilde is odd under is really this the reversal of the orientation or the epsilon, because of the epsilon tensor. One way to say it. Um, okay, so I guess let me just. I don't have. I won't have time to flesh out the formalism, but let me give you a definition of parity, a theory having a parity symmetry, which again plays really nicely with various dimensions, and especially when you're thinking about potentially anomalies in parity or the reflection symmetry in R. So there's a huge explosion in connecting sort of these topological ideas in 4D gauge theory to ideas in 2+1 dimensional theories to condensed matter systems. And one important role is played by the parity symmetry and anomalies in the parity symmetry. So you'll find a large amount of formal QFT literature thinking about parity or reflection symmetry. Okay, and the statement is parity is a symmetry if your QFT can be put on an unorientable manifold. Okay, so it's not going. I'm just going to give you a toy example and not flesh out why this is the case, and connect with the usual notion that we just take our local fields transforming x goes to minus x or a vector goes to minus a vector type things are under parity. But there's an invariant topological definition of this. Really, let's call it R, where if you want to posit R is a symmetry of the theory, then you can put that theory on an unorientable manifold. Okay, so let's very quickly think about an example, and then we'll move on to actual models. So let's go back to our example of 1 plus 1 1 plus 1 Maxwell. And let's consider the theory on a so it's not so it's a theory of one spatial and one time direction. So let's say this is the spatial direction x, and let's consider calculating a thermal partition function. So what we're doing is we're calculating. No, let's do it on a circle. So 1 plus 1 Maxwell on a spatial circle as we were doing before. So we have a spatial circle, and let's calculate a thermal partition function for this theory, which means that instead of just having a cylinder for going from initial time to final time, when we do a thermal partition function, we trace and we calculate in Euclidean time, and so this actually becomes a torus, which I don't know if I have drawing skills to draw a vertical torus, I'll draw a horizontal torus. Okay, so we have a theory which is one spatial dimension plus one time dimension. The spatial dimension is on a spatial circle, and usually what we're doing was we're calculating the partition function on a spatial cylinder. But when we're calculating thermal partition functions, we take the trace in Euclidean time, and so we identify the top circle with the bottom circle, which is the definition of a torus. Okay, so we're calculating a partition function on a torus for this theory. Torus is orientable, and so we can always calculate this partition function. So we can calculate this partition function for, in particular, when theta is 0 or theta is non-zero. Okay, so imagine that theta was non-zero. What we would have said is our interpretation for theta non-zero was that there's an electric field that is non-zero along the circle. We said, if you remember in our discussion for particle on a circle, we said the interpretation for a theta term was equal to the expectation value of f01, which is an electric field in this along the spatial circle. Okay, so now you can imagine if you have an electric field along the circle, and you want to do a parity transformation and try to understand if parity is a symmetry of this theory. So if you did a parity transformation, the parity transformation will flip the circle over. And now if you want to do a thermal partition function, what you would like to ask is, can you glue, and now my drawing skills are really going to come to bite me. Can we glue it in a way that you've seen a Klein bottle before, right? So imagine this is a Klein bottle. So instead of a torus, doing a parity transformation on the circle and gluing it back is gluing it with the opposite orientation, which would be a Klein bottle, right? So as long as theta was 0, there was no problem gluing it the other way. The electric field is just 0, so we could just glue it back, and we could phrase the theory on the Klein bottle, and the theory would still be well defined. When we have an electric field or a theta value, we can't glue it back after flipping orientation. So there's an obstruction to putting the theory on a Klein bottle, and so then we say that parity is broken. Parity is no longer a symmetry. It's a very complicated way to say things you already know. You could have said it in terms of A going to minus A, but this just wanted to give you a connection to how people think about anomalies. And if you want to think about anomalies in discrete symmetries, you won't get very far thinking about field transformations. You really have to think about putting things on non-trivial topologies. Okay? Good. All right, so let's think about, with all that generalities out of the way, let's think about solutions to the strong CP problem in explicit BSN theories that people have written down. Any questions about this? Two plus two. Oh God. So good. Well, I mean, I don't know. So the breakup into time and space is relevant when you really want to construct a Hilbert space. So you do a time slicing, and on that time slice you construct a Hilbert space, and you have some Hamiltonian definition of your theory. I don't know if there's the two time theory makes sense or not, but all of these things then can be said in the Euclidean in just the Euclidean signature, and then again flipping one coordinate flips the Euclidean orientation as well. So then the issue of signature is maybe issue of whether the theory makes sense with a Hamiltonian and time evolution, but everything can be phrased in terms of Euclidean path integrals, and then you just draw these pictures. And so that's the way people work in this field. Right. So in the standard model, theta or theta bar breaks Cp and P, as defined in the standard way, uh, left to right for parity and charge to minus charge for C. Um, and so if CP or P was a symmetry of the theory in the far UV, then given the fact that at least in the standard model, the CP violation in the weak sector and CP violation in the strong sector seem to be sequestered, gives us hope that maybe we can generate CP violation in the weak sector, but not generate CP violation in the strong sector, or that parity is badly broken by SU2 weak, but we can break it in a way. So we can start with a theory with parity symmetry, so we can have a left-right symmetric model where we have SU2 left symmetry and SU2 right symmetry. We have to break it down to see what to get the standard model, what we see. But we can break it down in a way that doesn't generate a big theta term in the Lagrangian, and maybe that is the explanation that we're seeing something which is close to zero or nearly zero is because actually in the far UV it is zero. The symmetries are pristine, and the effect of breaking is just small in the strong sector. Okay, so that's the philosophy of these solutions. And the standard problem that they run into is that the sequestering of CP or parity violation in different sectors breaks down as soon as you introduce the standard model, as soon as you introduce elements beyond the standard model. So we said in the standard model it's 7 loops divergent, 4 loops finite, but as soon as you write down any model that you can write down, you get a 1 loop generation of theta bar, maybe 2 loops. And you have to keep introducing structure to keep killing those terms. So at some point you ask yourself whether you're solving a problem or not. If you have, so I think I'll only cover, so parity solutions. Classically, there's papers by Babu, Mohapatra, which involve extra gauge structure and mirror fermions to double this SU2 left sector into an SU2 right sector, and so those are intricate models. What I'll focus on are models that use so-called CP symmetry, and they're sometimes called Nelson bar models. The problems faced by both of these models are very similar qualitatively. We write down a simple manifestation of the model. We'll find that we'll have to impose a lot of symmetries to kill other terms that we could have written down, even then at tree level, even which would spoil our solution. And even once we do that, at loop level, these would be generated, and we would have to keep introducing structure. Okay, so I'll give you the simplest version of the Nelson bar model to illustrate the challenges. Very quickly. So we add to the standard model the following particles. Well, I guess it includes the standard model. How does the subset sign look like? This is a subset, right? The other way around? Are you sure? Okay. So these are the. Let me write down the Lagrangian, and I will tell you what we're adding to the standard model on top. So what we've added to the standard model is one vector-like pair of quarks, Q conjugate. So quarks meaning these are 3 bar under color. So fundamental, anti-fundamental of color, and they have electric charge 1/3 minus 1/3. So similar to down type quarks, and indeed the idea would be to provide mixing with the down type quarks. I've written down explicitly the standard model Yukawa matrix for the down type quarks. So this is by down. So the I, J indices are just standard model flavor indices, 3 by 3 flavor indices. And then we've also added standard model singlet scalars, some number of them labeled by this index A. It doesn't really matter how many you add. You can add only one, you can add more. If you add only one, you run into problems sooner. If you add more, you can run into problems a little later. But they're all standard model singlets. And their interaction with the standard model down-type quark looks like that. The theory is assumed to have CP exact, so there's a basis in which all the couplings can be made real. And then we say CP violation is through some eta A's, so there's a potential for eta A's that we're not writing down. The potential is such that you get complex webs for these eta A's. So etas violates CP spontaneously through complex vacuum expectation value. Okay, so we start with all real couplings. So delta CKM is 0. There's no Yukawa couplings don't have any phases right now, and the idea would be to see, and also of course theta is 0 as well. The idea would be to see what is the level at which we generate YCKM and the level at which we generate theta, and whether we can actually get one to be order 1, then the other to be 0 or very small. Good. So let's define, so etas are going to get webs, and so let's define this parameter bi, which is just going to be the sum over a, the web of eta is. Okay. So here sum over a is implied. I guess everywhere sum over a is implied. So defining this parameter, we can write down the quark mass matrix. We have a 4x4 matrix for the 3 standard model quarks, and one of these guys. Something like Q1, Q2, Q3, if you will. There's a term mu here. It's B1, B2, B3. I run out of space here. Q conjugate D1, D2, D3. So the down type quarks have a mixing. Crucially, these elements are 0. There's no mixing between these quarks and Q conjugate. And this 3x3 block is whatever real Yukawa you started out with, times V, the Higgs web. Okay, so schematically, the form of the mass matrix looks like 0, and the 0 is mu B0 MD, this being a 3x3 matrix, and the 0 here is crucial, because the 0 tells you that even though, so B's are in general complex, that's where CP violation is coming from the complex webs, but even though B's are complex, because of the 0 here, arg det M remains 0. So that's the sort of basic idea of getting theta bar to remain 0. You introduce CP violation in a way that doesn't contribute to the determinant of the mass matrix. Okay. So let's see what the CKM, well, qualitatively at least, let's try to see what these models will predict for the CKM, and at what level would theta bar be generated, again, qualitatively. So by the way, one challenge is to ensure that the Lagrangian that we wrote down are the only terms allowed. That's not true just by gauge invariance. There's other gauge invariant terms we could write down. So to prevent other terms from appearing, in addition to CP, we would have to posit other symmetry. So you usually have to posit some Zn symmetry or Z2 symmetry to make sure the 0 is actually indeed 0, and already at tree level, you're not spoiling the solution. So there's various restrictions that I guess we'll talk about in just a second, that you have to impose for this, even the mechanism to get off the ground. But let's look at qualitatively what the CK matrix would look like. So that when you diagonalize the quark mass matrix, you diagonalize this matrix, which looks like mu squared plus And if we assume that mu squared plus b dagger is much bigger than the down type quark masses, um, then we can integrate out the heavy quarks, and then just produce a effective mass matrix for the light 3 quarks that are left in the standard model. Okay. So again, for this choice of parameterization, we can write down the quark mass matrix. The down type quark mass matrix in this model would be given by something like something you get by just sort of doing a perturbation theory by integrating this out and keeping track of the mixing between the heavy and the light guys. So this is now in general not a real matrix. MD was a real matrix, but now this has complex phases in particular. It has these phases coming from B. And although argdet M is still 0, so we have at least at tree level, we have a complex matrix for the quarks, but we don't have theta bar. So at tree level, at least given the structure of the Lagrangian we wrote down, we seem to be in business. It turns out that if mu is much bigger than the, these quantities BF, or BF has say 2 small quantities and 1 large quantity, something like this, then in both those cases, if you diagonalize this matrix and calculate what the CKM matrix actually looks like, you find that delta CKM actually is really small. Okay, the details are not super important. Just want to highlight qualitatively how much work you have to do to get these models to work. So if you have something like this structure, you get delta CKM is order B over C, etc. So in order to get going even at tree level, we have to make sure that we have some hierarchy of scale so that we can integrate out these quarks so that we get a unitary, unitary CKM matrix. And then we have to make sure that the diagonalizing matrix doesn't have hierarchies such that the CKM matrix that comes out is too small, and so we should have a structure, certain size structure in the theory. Sorry, question. Oh, it's probably one of them is an L. Sorry. Yeah. Still. Not good. I was fine before. I think this is what's supposed to be. It's a 3x3 quark matrix that you would get, quark matrix quantity that you get once you do the integrate out the one extra flavor, heavy flavor. Okay. Yeah. That, I mean, I can when I give you the references, you can look up the expressions in the references. The idea being that you need not just need the structure, but you also need coincidence of scales. So for example, mu should be somewhat less, but not much less than these quantities to actually get a reasonable. You're doing diagonalization. If there's a big hierarchy, then in big hierarchical matrices, the eigenvalues are usually there's not a big rotation that you need to do to diagonalize, and so you don't actually get the right CKM structure. So you need some matrix which is roughly the same commensurate order in different mixing and the diagonal matrices to get big mixings and CKM. So you need a reasonably intricate structure to actually get going, and at tree level, okay, let's leave that up. At tree level, you already need to forbid certain interactions that will kill the solution, and so at tree level, you forbid dimension 4 operators that you could have written down, dimension 4 gauge invariant operators like um, these, which we didn't write down. We could write down interaction of the Higgs with these interactions, um, and not to say that we've introduced a bunch of new fundamental scalars in the problem, so ideally they should have a large quadratically divergent mass. So even already at the renormalizable level, you have these issues. At dimension 5, you would have operators which, so people typically impose some kind of Zn symmetry on the eta so that you can kill this particular term. But then there's terms like dimension 5 terms like eta star eta QQ conjugate, and these are invariant under the Zn symmetry. So these are hard to kill. And remember, theta bar was 10 to the minus 10. So you really can't afford one or two loop or dimension 5, dimension 6 operators generating theta bar for you. So you have to ensure, again, put more structure to make sure dimension 5, dimension 6 operators are, dimension 5 operators are absent. And finally, there's almost always a one loop, if not one, then two loop contribution to theta bar. So this is just a generic feature of all these models that you can play with some intricate structure to at least say technically, naturally, I've said tree level I don't generate any theta bar because I have enough symmetries at my disposal to kill it. But at loop level, you run out of steam in almost all models that I know of. So there are models where there are contributions which look like this from quartic interactions of the Higgses. Let me draw them. So if you're, this is a Higgs, I guess this is a eta. So if your Higgs and eta have, again, renormalizable interactions, H dagger H, eta dagger eta, with some quartic coupling here. At one loop, you'll generate these diagrams with complex quark mass matrix, and this does not any longer have arc that m equals 0, and so you would generate a theta bar at one loop level. And there's also an analogous diagram at two loop, which is just quartic interactions between eta to the fourth, between etas themselves, which would have to be present if you want to spontaneously break the symmetry. So so you see that once you add even the simplest possible model, just one extra flavor of vector-like quarks to mix in and generate a CP violating term, there's tons of structure you have to introduce to actually make sure theta doesn't get generated. There's no more any sign of the sequestering of 6 loop, 5 loop, 6 loop contribution to theta. At one loop, at tree level, you start getting contributions to theta right away. And so for all models of this kind, this is a generic problem. You introduce enough things that you actually mess up this structure of the standard model. So there are very few compelling models of this kind that work. Let me just give you one qualitative feature that is worth mentioning in the context of this model building toolkit. And then we move on next time to axion solutions for the strong CP problem. So the one interesting mechanism that is usually used in conjunction with these to avoid generation of theta bar at loop level is to study. So sometimes it's called the Hiller-Schmalz mechanism. And there's an equivalent mechanism in extra-dimensional systems that I'll mention again qualitatively. Okay, so the Hiller-Schmalz is in the context of supersymmetry, and and the and the basic idea is the following: it is to notice that in supersymmetry there are non-renormalization theorems for terms arising from the superpotential, such as the Yukawa matrices. Okay, so I'm not going to go into great detail here, uh, but emphasize the qualitative nature of the solution. So the idea is that in supersymmetry, renormalization of there's non-renormalization theorems for superpotential, basically arising from the fact that the superpotential is holomorphic, and so often there aren't any holomorphic contributions that you can write out of the superpotential. In particular, if you ignore wave function renormalization, then the beta function for the gauge coupling is one loop exact. So this is called the NSVZ beta function sometimes. Okay, so ignoring wave function renormalization, and we'll talk about wave function renormalization in just a second. That's why I've made them explicit here in the Lagrangian. The beta function is just one loop exact, and it does not generate, does not change the theta angle, because it's just a real contribution to the beta function is just this, and it does not generate a theta angle. So if you had a system which actually was supersymmetric, and there was a reason, maybe CP, maybe parity in the UV, that that the theta was 0, at least the superpotential renormalization of the gauge coupling or the Yukawa couplings does not generate a theta angle. Okay, so that seems like a qualitative win. We have a protection from these non-renormalization theorems for the theta angle. And what about the wave function renormalization? The wave function renormalizations are in general complex. They're not holomorphic, but they're Hermitian. Are positive Hermitian matrices. Okay, so for example, if you wanted to canonically normalize these fields, let's say Z's are arbitrary, complex, but positive Hermitian matrices, you could do a rotation, something like Q goes to some T times Q. This is the T is some matrix, and T is again a positive definite matrix. So, so you can, for example, choose parameters such that the up type quark rotations are something like mu. If you had a model which gave you only diagonal flavor blind contributions to the up type matrices to rotate, but the down type matrices was something like VCKM. Then when you do this rotation to canonically normalize the fields, you would actually get the CKM matrix without ever generating a theta term. So what's the mechanism? The mechanism is that if you have a Hermitian matrix, it could be complex, but the det of that matrix is not the determinant of the matrix is real. And so if you have models where all complex numbers arise through wave function renormalization, like in supersymmetric models, the wave function renormalization is gives you Hermitian matrices, and when you canonically normalize your fields to go to the canonical basis, the Yukawas you pick up have the structure that they don't generate a theta bar term, but they do generate a CKM phase. So that is an extra bit of mechanism that you could use, and people have tried to use to patch onto models of Nelson bar or Babu Mohapatra to try and see whether we can solve the strong CP problem. The trouble with these models, and by the way, the extra dimensional model, the models that was written by Lisa Randall and collaborators have a very similar feature where the CP violation doesn't come from the Yukawa sector, but it comes from wave function of the fermion in the extra dimension. And so there's a very nice, simple model of that kind. Again, using the mechanism that wave function normalization can give you CKM matrices, but it doesn't give you, being Hermitian, it doesn't give you a theta bar. The problem with these mechanisms comes about, for example, for the Hiller-Schwarz, you actually now contemplate the real world where SUSY is broken, and so you have SUSY breaking terms, and SUSY breaking terms generically then spoil this. You don't no longer have this non-renormalization theorem when SUSY is broken, so you have to impose conditions on SUSY breaking patterns. You typically need some kind of flavor structure, flavor blind SUSY breaking, SUSY mediation mechanism like gauge mediation. You still have to worry about various phases that can arise in SUSY breaking. So at the end, again, there's not a super compelling model that arises, but there's a qualitative mechanism here. So maybe one of you can write a nice, beautiful model that solves the problem. So the upshot of discrete symmetry solving the strong CP problem is, I think, in principle, it's a class of solutions, so we should take it seriously. We should understand whether it can be made to work or not. Most models seem to run into problems as soon as you compute one loop, two loop processes, and the theta bar they generate is really large. The phenomenological downside of these models is that, depending on your personality, it's a downside that these mechanisms could play out far in the UV. You could have in principle, you could have CP symmetry at the Planck scale. The CP violation from these etas, for example, could be at 10 to the 10 GeV scale. And in the low energy theory, you just have very small theta bar in the standard model and nothing else. So you'll almost never see in any collider experiment ever a signal of a Nelson bar solution to the strong CP. So that's maybe a negative aspect of these solutions, but we would like to understand if that possibility exists or not, whether we'll see the solution of the strong CP problem in our low energy detectors. So we want to understand if there are compelling solutions like this, but it seems like they're really hard to construct. And there's some interesting mechanisms that might be brought to use on these models. But the next time we'll start with the axion, which actually has which predicts a low energy signal that is at least kinematically accessible to any experiment that we can build. And so that's where we'll start next time.